Okay, so we wish to prove the following strengthened version of Casorati-Weierstrass. So this is the statement that we want to prove. So what we have is we've got an essential singularity at A, meaning that, so that tells us by Casorati-Weierstrass that the image of every ball is dense in C. Okay. Let's say F maps to here. And if we pick any C in the complex plane and we take an epsilon bigger than 0, then this says that given a delta, so we've got an epsilon ball here, right? So given a delta here, I claim that there exists an alpha in this ball. So it might not be C, but it's somewhere close to C, so this alpha, such that I can find infinitely many points in this delta ball that gets mapped to alpha. Okay? Notice that in particular, this implies that if f of z equals w has at most n solutions for all w in C, then z0 is a non-essential singularity. Okay. Because if this wasn't the case, then we'd have that there exists a w in C such that f of z equals w has infinitely many solutions. No, sorry, that's not what I meant. This is true because if z0 was an essential singularity, then we'd have, well, in particular, we'd have an epsilon, well, an alpha, and in fact, it turns out that we can almost pick any alpha we want. Well, this alpha plays the role of w, where we have infinitely many solutions. So this certainly implies that. Okay, this is much stronger. So anyway, what's the proof of this? So the proof is rather intricate. Okay, so there are a couple of ways to do this. So solution 1. Suppose that the assertion is false. So suppose that there exists a C and a delta bigger than 0 such that for any alpha in the ball of radius epsilon center C, f of z is equal to a has finite number of solutions in ball radius delta center A, remove A. Okay? Now, what we do is the following. For all n bigger than or equal to 0, define the subset an, which is a subset radius epsilon center C, right, where we define an to be all alphas in here such that f of z equals alpha So what are we doing here? So since this is finite, right, there are a finite number of solutions, then we can define such sets, right? It allows us to define such sets. So A1, for instance, A1 would be, so, you know, we picked our point C in our target space, right? There exists a C, and then there exists a delta with the following property. So assuming this forces us to choose a bad choice of C and a dangerous choice of delta. Okay, so there exists such choices, and we have that any alpha in this ball has the property that it has finite number of solutions. So that means that some of these points, some of these points are going to have one solution, some of these points are going to have two solutions, and so on and so forth. But the point is that essentially if we take the union over all n, we're going to get the entirety of the ball. Okay? Now, claim. My claim is that for all n bigger than 0, these ANs are closed B epsilon C. Okay, each of the ANs is closed. Proof? Let AK belong to AN. Okay, and suppose that AK converges to some alpha B epsilon C. Okay, so each of these alpha K's have the property that f of z is equal to alpha K has at most n solutions. So my claim is that the limiting value is going to have at most n solutions as well. Okay, well, suppose that alpha is not in AN, right? Suppose that the sequence actually leaves the set. We're going to get a contradiction. There exists big N and little n such that, oh, okay, Zn. Well, okay, if alpha doesn't belong in A, okay, so here's the point. These sets are actually nested, aren't they, right? So all the points that have at most one solution, in particular, have at most two solutions. All the points that have two solutions, in particular, have at most three solutions, and so on and so forth. So that means that if alpha doesn't belong to AN, then it can't belong to the union AK up to AN. So that means that there exists a big N greater than N, such that we've got this many solutions. Now, what we're going to do is we're going to let R be bigger than 0, such that the ball radius little r, zj, sits inside this set here. Okay, so, and this is for all j, okay? So there exists a small enough ball that, okay, so there's a delta right here, z1, z2, up to zn, right, and there exists a little r such that it sits inside every single one, okay? We're taking a j such that this holds and that each of these balls are pairwise disjoint. Okay? Now, these are all open sets, so by the open mapping theorem, this is open as well. Okay, so it's a neighborhood of alpha for each j. It's an open neighborhood for all alpha because each of these guys get mapped to alpha. Okay? So that means that there exists an eta bigger than 0 such that the ball, right, so each of these guys are open, right, and they're a neighborhood, right, they're an open neighborhood. So if I take the intersection of these finitely many guys, I'm going to still get an open neighborhood of alpha, right? And since this is open, then I can fit in some open ball inside it. Now, if K is chosen such that alpha K is actually less than R. Okay, so what does that, so what is the next bit of argument? So I think this is actually a typo. If you choose K such that, so essentially we've got alpha K going to alpha, right, the limit. So in particular we can choose a K such that this holds, right, because this is an accumulation point, right? So this is supposed to be eta, I think. They wrote it as R. I think it's supposed to be eta. So suppose that I choose, so since the alpha K's go to alpha, there exists an alpha K. In fact, there exists infinitely many of them, such that this holds. Okay, cool. So let me choose such an alpha K. Well then, if alpha K is in here, then that means that alpha K belongs to the right-hand side. And so it belongs to this for all j 1 through to n. So that means that for all j going from 1 to n, there exists a tj such that f of tj, there exists a tj in this guy, which is a subset of b delta of a remove a. So there exists actually tj in this guy right here, such that f of tj is equal to alpha k. And this is a contradiction. And notice, actually, you might say, hang on, what if I have repeats, right? Well, the key is that actually we took R to be small enough that these are all disjoint. Okay, so we have distinct solutions, right? It's nothing to do with multiplicities, it's just distinct solutions. So that's a contradiction, right? So that means that actually, so if alpha has more than n plus 1 solutions, then just take, some element in your sequence that's close enough to alpha, then that would end up having more than n solutions as well. My question is actually, is the number of solutions like a local constant then? Anyway, so we've proven that. Okay, so what have we got? Okay, so what have we got? We've shown that an is closed. Of course, we've only shown that it's closed in this, but that's all we care about. And we've also got, of course, this. Now, we use the bare category theorem. So what was the bare category? What did the bare category theorem say? Okay, so basically the bare category theorem, one statement of it says that it basically tells us that a complete metric space is big, right? That if you have a countable collection of nowhere dense subsets, then you can't possibly recreate the entire space by that. Some of them would have to be not nowhere dense. What did nowhere dense mean? It meant that sets whose closure has empty interior. Now in this case, ANs are all closed, so the closure of a closed set is the set itself. So in this case, we're saying that since AN, since you can form this ball right here, this open ball, which is still a complete metric space, right? So it's a complete space, and these are all closed. And that means that there must exist an n such that an does not have empty interior. Okay, so interior is non-empty, right? So there must exist an an such that you can fit a little open ball inside the an. Okay, if you can fit an open ball inside the an, that means that you've got an entire open set of points which has exactly n solutions. All right, so why is this a contradiction? well, we still have to do a little bit more work, okay? So let's take, so under these assumptions, we're carrying on. Let's take C naught in AN and epsilon naught bigger than 0 such that the ball centered at C naught with radius epsilon naught sits inside AN. Okay. Now let AN be the maximum number of pre-images of alpha under F. Okay, as alpha ranges through this open set. Okay, so maximum number of pre-images just means that, you know, M is the, so basically you let F, so essentially you've got this open ball right here, centered at C naught, okay, and this sits inside AN, okay? So that means that every single point here gets mapped, well, every single point here, sorry, I want to say, so where am I working in? Yes. So every single point here, right, has at most n solutions, okay, and no more because it sits inside AN. So that means that if I take a particular point and take the pre-image, then it's going to have at most n points in its pre-image and none more, okay? So I can imagine, you know, looking at every single point here and taking essentially a supremum, right, over all the points in here, but that's just going to be a maximum because the possible outputs would be 1 up to n, right? So if you want to be really careful, we can define a function, right? We can define a function that maps from this set to 1 up to n with the property that phi of z is equal to the number of elements of the pre-image of F, right? And this is going to be 1 up to n because this sits inside AN, okay? And then we can let M be the supremum over all Z in this guy, a phi of Z, but that's just going to be the same thing as a maximum, right? Because the range is a discrete set, right? It's 1 up to n. So we can call that, we can let that, yeah, so we call that M. All right. Now, of course, okay, so it could turn out actually that none of these points have n solutions. That's not problem because, you know, this ball doesn't have to be the entirety of AN, of course, right? So it's no contradiction, right? If all of the points here have one solution and, you know, points out here have n solutions, for instance, or points here have 0 solutions, but points here have n solutions. What can't happen is there to be a point inside here that has n plus 1 or greater solutions. That can't happen. However, if we looked at this function, right? If we took the maximum, the M of this entire set AN, of course we would have to get n. Now, we can choose okay, so let alpha, so choose an alpha. So choose an alpha in this such that there exists m points and exactly m points, z1 up to zm. So z1 up to zm in the ball of radius delta in A. So this is going back to the, you know, the source space, and we're in the target space here, such that f of zj is equal to alpha or J1 up to M. Hang on, but why should such an alpha even exist? No, remember M is not N, right? It's the maximum, so this obviously there will be an alpha, otherwise the maximum wouldn't be M. So that's fine. Okay, so the reason why we define this is that we can't say choose Z1 up to Zn because we don't know if there are going to be N solutions in here, right? All of these could be less than N, so that's why we defined M. Okay. Now, there exists an R and an eta greater than 0 such that, again, as before, BR of Z1 up to Zn are pairwise disjoint, and that this holds. Right, we use the same argument as before, applied to alpha now. The contradiction came when we took an alpha k that's within R, but we're not going to do that now. Okay, so that's perfectly fine, right? We've already talked about this. Okay, so what does this mean? This means that each point in okay. So this guy, however, implies that if I take any point W in this set, then there are at least M preimages in B delta A, remove A. Why is this? Okay, I think this is another typo. This implies that there are at least N, big N preimages in this set right here, right? Why? Let's take W in this set. Then for all J from 1 up to N, there exists a psi in BRZ, which sits inside B delta of A, remove A. And again, all these psi J's have to be distinct because all of these balls are distinct, such that f of psi J is equal to W. So we have at least N preimages in this for W. Okay? W has at least N preimages in this. Okay. Now on the other hand, B eta of alpha is a subset of B epsilon naught C naught. Okay, I'll just talk through the rest of the proof because I'm starting to not understand it. Since this holds as well, I'm not sure why this holds. By the definition of M, W has at most M preimages in this set right here. Okay. Therefore, if W is in this, then the only solutions to f of z equals W must lie in the union of these disjoint sets that we already talked about. Okay? Now, if we choose S so that S is the minimum over all j of the zj's minus a minus r. So we've got a whole bunch of, balls here, and we're taking an S where Bs of A is disjoint from the union of all of these guys. So we're fitting this was our original delta ball. This was our balls of radius r centered at each of the zi's. We're taking a ball that sits inside here like that. So these are all disjoint. Okay. Then that means that if W is indeed in this, then there are no solutions to f of z and w which lie in, oh okay, so it's centered at A now. So actually we're taking an S such that it's even smaller, and we have no solutions to that, which contradicts the Casorati-Weierstrass theorem. Okay, and that's done. The second solution is far quicker, and let's actually do that now. Okay, so what's the other proof? So let's say this again, right? So what were we trying to prove? Let's remind ourselves. So we want to prove that if C is a complex number and epsilon is bigger than 0, then for all delta bigger than 0, there exists an alpha in the target space, I like to call that, in the target space. Nope. The target space here, such that f of z is equal to alpha has infinitely many solutions in B delta A. Okay, now what's the proof of this? So for all n bigger than 1 over delta, so okay, so what do we do? So this actually proves it directly, which is quite exciting. So let delta be given. Okay, so let C in C epsilon bigger than 0 and delta be given. I want to show the existence of such an alpha. Okay. Well, for all n bigger than 1 over delta, we define Gn to be f of the ball radius 1 over n centered at A minus this. Okay. Right, so this is the crucial bit, right? Okay, so we've got A here, right, which is an essential singularity. Okay, we've got our delta that's been fixed, right? You've chosen a delta, we've picked a delta. Okay, so what I'm doing now is I'm going to take a sequence of balls that get smaller and smaller and smaller, that shrink in radius. Okay, and I define G of n to be the image of all these guys. Okay, so, it's going to be the image of all these guys. Now, the GNs are all open, of course, by the open mapping theorem. And GN is dense, so GN are all dense in C. Okay? So, here's the really cool thing. Bare category theorem says that the intersection of all these guys is dense. Why? Let's see the bare category theorem again. Okay, so this is the bare category theorem here. So each of these GNs are dense. Okay, so we've got, and these are all open. So there you have it. We've got a countable collection of open dense subsets, and quite conveniently, it's the same letter as well, which is quite rare. So we know that the intersection of all these guys must be also dense in X. Okay? So, well, okay, so if the intersection are all dense in X, what does that mean? well, okay. So this being dense in X, let me call this G, just like we do in the theorem. This being dense in X means that for all X in X, there exists a G in G, such that, and for all epsilon bigger than 0, G minus X is less than epsilon. So let epsilon be given as in the question, right? And let us call G, let's call it alpha instead. Okay, and let's call X C. Okay, so we've got that there exists an alpha in C such that this holds right here. Now, so alpha in G such that this holds. Now alpha belongs to Gn for all n in N, and that means that alpha belongs to this set for all n in N. And that means, therefore, that there exists, so that means that for all n in N, there exists a psi in the ball of radius 1 over n that's not equal to A, such that, now, this holds for all n in N, right? So this holds for all n greater than or equal to n, well, okay, greater than or equal to n, where n is, 1 over delta, right? Though actually we've assumed that n is bigger than 1 over delta, but let's say that again. So, so for all n with that property, there exists a psi in this such that f of psi is equal to alpha, and that means that there exists a psi in B delta A minus A such that f of psi is equal to alpha, and that's the proof. There are infinitely many. Done. Very, very elegant and very fast, this second way. Okay, so it's not always necessary to go by contradiction.